Okay. Okay, so let's start with electrochemistry first. So, okay, in this chapter, you will look at the process of electrolysis and the industry based around the process of electrolysis. You'll look at the electrolysis of various substances in the molten state and in aqueous solution. You will see how useful electrolysis is across manufacturing and fuels production industry by considering the extraction of aluminium, chlor-alkali industry, and the industry based around electroplating. Okay, so first, electricity and chemistry. First, what is electrolysis? So electrolysis is the breakdown of an ionic compound, either molten or in solution, by the passage of electricity through it. The substances that is decomposed is called the electrolyte. An electrolyte is a substance that conducts electricity when in the molten state or in solution. And next, the electric current enters and leaves the electrolyte through electrodes, which are usually made of unreactive metals such as platinum or the nonmetal carbon, graphite. These are said to be inert electrodes because they do not react with the products of electrolysis. The two electrodes are the cathode and the which are the negative electrodes, and which attracts cations is the positive charge ions. And the anode is the positive electrode, which attracts anions, which is the negatively charged ions. Okay, next. Electrolysis of lead bromide. So, if you can say this one. Okay, so it shows that solid lead bromide in a crucible with two carbon electrodes in contact with it. When the electrons are first connected, the bulb does not light up because of the solid compound does not allow electricity to pass through it. So, however, when the compound is heated until it is molten, the bulb does light. The lead bromide is now behaving as an electrolyte. When this happens, an orange red vapor is seen at the anode and lead metal is produced at the cathode. Lead bromide is binary compound, and binary compound are those that contains two elements chemically combined. Generally, when molten binary compounds such as lead bromide are electrolyzed, metals such as lead are formed at the cathode, and also nonmetals such as bromine are formed at the anode. The passage of an electricity current in the process of electrolysis results in the break up the composition of lead bromide into its constituent elements. And so the equation is PbBr2 equals to Br2 gas plus PbL, which is this one. Okay. Next, electrolysis of aluminum oxide. So aluminium is the most abundant metallic element in the Earth's crust. It was discovered in 1825 by Hans Christian Ørsted in Denmark, but was first insulated by Friedrich Wöhler in 1827. It makes up 8% of the crust and is found in the mineral bauxite, chrysolite, and mica, as well as in clay. So today we use aluminium in very large quantities. The annual production in the world is 19.5 million tons. The commercial extraction of aluminium has been possible by two scientists working independently of each other, who discovered a method using electrolysis. The two scientists were Charles Martin Hall, which is in USA, and who discovered the process in 1886, and the French chemistry Paul Héroult, who discovered the process independently in the same year also. They process the process of they develop, often called the Hall-Héroult process, involves the electrolysis of aluminum oxide, alumina, which is called alumina also. The process involves the following stage. So, bauxite, an impure form of aluminum oxide, is first treated with sodium hydroxide to obtain pure aluminum oxide, removing impurities such as iron oxide and sand. This improves the conductivity of the molten aluminum oxide. And the purified aluminum oxide is then dissolved in the molten cryolite Na3AlF6. Cryolite, a mineral found naturally in Greenland, is used to reduce the working temperature of Hall Herold cell from 2017 degree, the melting point of pure aluminum oxide, to between 80 and 1000 degree. Therefore, the cryolite provides a considerable saving in the energy requirements of the process. And in recent years, it has become necessary to manufacture the cryolite. The molten mixture is then electrolyzed in a cell similar that's shown in this figure, such as this one. Okay. And the anodes of this process are blocks of carbon, which is graphite, which are lowered into the molten mixture from above. The cathode is the graphite lining of steel vessel containing the cell. And aluminum oxide is an ionic compound. When it is melted, the ions become mobile, as the strong electrostatic force of attraction between them are broken by the input of heat energy. During electrolysis, the negatively charged oxide ions are attracted to the anode, which is the positive electron, where they lose electrons oxidation. Okay, next. Using cheap electrical energy has allowed aluminum to be produced in such large quantities that it is the second most widely used metal after iron. It is used in the manufacture of electrical transmission cables. Aluminum strands are wrapped around a core of steel wires. Aluminum is also used because of its low density, chemical inertness, and good electrical conductivity. This means that it will take a high voltage and low current to carry the same power, owing to the first two of these properties of aluminum. It is also used for making cars, bikes, cooking foil, and food containers, as well as in alloys, such as duralumin, which is used in the manufacture of aeroplane bodies. Worldwide production of aluminum now exceeds 40 million tons each year. So how do you recycling aluminum? The metal aluminum is the third most abundant element in the Earth's crust after the non-metal oxygen and silicon, and the most abundant metals in the Earth's crust. However, it is more expensive to produce than many metals, such as iron, due to the cost of the large amounts of electricity, which are needed for electrolysis process. As a result, globally, up to 50% of the aluminum used is recycled. Obtaining aluminum from recycled scrap requires approximately 5% of the energy needed to extract aluminum from its ore. However, it should be borne in mind that collecting scrap metal and transport the metal extraction plants add extra cost to the overall recycling cost. There are serious environmental problems associated with the location of aluminum plants, so including the effect of the extracted impurities, which form a red moon, which is this one, and the fine cryolite dust, which is emitted through very tall chimneys, so as not to affect the surrounding area. And last, the claim link between environmental aluminum and the degenerative brain disorder called Alzheimer's disease. It is thought that aluminum is a major influence on early onset of this disease. However, the evidence is still inconclusive. And okay, next is the electrolysis of aqueous solution. Other industrial processes involve the electrolysis of aqueous solution. To explain what is happening in this process, we will first consider the electrolysis of dilute sulfuric acid. Electrolysis of dilute sulfuric acid. Upper water is a very poor conductor for electricity because there are few ions on it. So, however, it can be made to decompose if an electric current is passed through it in a Hofmann voltameter, as this one. This is the voltameter. To enable water to conduct electricity better, some dilute sulfuric acid or sodium hydroxide solution is added. When the power is turned on and an electric current flows through this solution, gases can be seen to produce at two electrodes and they are collected in the side arms of the apparatus. After about 20 minutes, roughly twice as much as gas is produced at the cathode. As at the anode, the gas collected at the cathode burns with a squeaky pop, showing it to be a hydrogen gas, which is 4H plus 4E minus, which is 4 electrons minus, equals to 2H2 gas. If during this process, the water molecules lose hydrogen, then the remaining portion must be hydrogen ions, which is OH minus, and these ions are attracted to the anode. Generally, when aqueous solutions are electrolyzed, hydrogen is produced at the cathode and non-metals other than hydrogen are formed at the anode. This experiment was first carried out by Sir Humphrey Davy. It confirmed that the formula for water was H2O. In the electrolysis of dilute sulfuric acid, platinum, an inner electrode, may be replaced by carbon graphite. The only difference to occur is that, as well as oxygen being produced at the anode, a little carbon dioxide also will be formed. Next, electrolysis of concentrate aqueous sodium chloride. So, when the sodium chloride is dissolved in water, the ions present become free to move. Because when concentrated aqueous sodium chloride is electrolyzed, the two gases, hydrogen and chlorine, are produced. Sodium might have been expected to be produced at the cathode. Why does this not happen? Because the four ions are present in the solution from water H plus and OH minus. From sodium chloride, Na plus and Cl minus. When the current flows, the H plus ions and the Na plus ions are both attracted to the cathode. The H plus ions, however, accept electrons more easily than the Na plus ions, and so hydrogen gas H2 is produced at the cathode. Because the sodium is more reactive than hydrogen, so electrons more easily. Generally, it is found that during the electrolysis of aqueous solution, very reactive metals like sodium are not formed at the cathode. OH minus and Cl minus are attracted to the anode. The Cl minus ions give up electrons more readily than the OH minus ions, and so chlorine gas is produced by the electrons and electrons and water. Okay, electrons process. These leave a high concentration of hydrogen hydroxide ions, OH minus AQ, which is aqueous, around the cathode. The solution in the region of the anode therefore become the alkaline. Okay, so here are some electrolysis guidelines. So first, nonmetals are produced at the anode, whereas metals and hydrogen gas are produced at the anode in the cathode. At an inner anode, chlorine, bromide, and iodine, the halogens, are produced in preference to oxygen. At an inner cathode, hydrogen is produced in preference to metals unless unreactive metals such as copper are present. Okay. Okay, so I'll be explaining about fuel cell. Scientists have found a way of changing chemical energy into electrical energy using a fuel cell. Fuel cells are chemical cells, except that the reagents are supplied continuously to the electrodes. The reagents are usually hydrogen and oxygen. The fuel cell principle was first discovered by Sir William Groove in 1839. So when William Groove was electrolyzing water and he switched off the power supply, he noticed that a current still flowed, but in the reverse direction. The process was explained in terms of the reaction at the electrode surface of the oxygen and hydrogen gases which had been produced during the electrolysis. The hydrogen fuel cells used by NASA in the US space program are about 70% efficient, and since the only products water, they are pollution free. So take notes here, a hydrogen oxygen fuel cell use hydrogen and oxygen to produce electricity with water as the only substances produced. Okay, and the advantages and disadvantages of the hydrogen fuel cell is fuel cell technology has its advantages. For example, a fuel cell uses hydrogen and oxygen and makes non-polluting water in the process of generating electricity, whereas petrol and diesel engines produce many pollutants. And it is similar to a battery, but does not require any external changing. And it is also capable of producing electricity as long as hydrogen fuel and oxygen are supplied. And the disadvantages to using fuel cell is hydrogen is in the gas state at room temperature and pressure, so it is difficult to store in a car. It is difficult to store in a car. The fuel cell and electric motors are less durable than petrol or diesel engines, which means they do not last long. And fuel cells is also very expensive at this moment. Okay, next, electroplating. Electroplating is the process involving electrolysis where one metal is plated or coated with another. Often the purpose of electroplating is to improve the appearance of the object and give protective coating to the metal beneath. For example, bed taps are chromium plate to prevent corrosions and at the same time are given a shiny, more attractive finish. So technically, electroplating is applied to metals to improve their appearance and resistance to corrosion. Okay, so an example is silver plating a spoon. So the silver ions are attracted to the cathode where they can electron like this. Okay. So plating plastics. Nowadays, it is not only metals that are electroplate. Plastic has been developed that are able to conduct electricity. For example, the plastic poly can be electroplate in the same way as the metals we have discussed earlier before. Okay, so I'm done with electrochemistry and we'll discuss about the chemical energetics, but not including the exothermic and endothermic reactions. So the substances from petroleum is example like this. So like car, motors, and airplane, ships, and bus. They are all used liquid obtained from petroleum as fuels. So technically, petroleum is a mixture of hydrocarbons. Oil refining. Petroleum, also called crude oil, is a complex mixture of compounds known as hydrocarbons. Hydrocarbons are molecules which contains the elements hydrogen and carbon bound together covalently. These carbon compounds form the basis of a group called organic compound. All living things are made from organic compound based on the chains of carbon atoms similar to those found in petroleum. Petroleum is not only a major source of fuel, but it is also a raw materials of enormous importance. It supplies a large and diverse chemical industry to make dozens of products that we use in everyday life, such as polymers and medicines. Hydrocarbon is a compound that only contains hydrogen and carbons and not other elements. Petroleum is not very useful to us because until it has been processed, the process known as oil refining, it is carried out an oil refinery. Refining involves separating petroleum into various batch or fractions. Chemists use a technique called fractional distillations to separate different fractions. This process works in a similar way to discuss in the chapter 14, in the chapter 14, we haven't learned that, for separating ethanol, alcohol, and water. The different components, which is fractions, separate because they have different boiling points, and the petroleum is heated to about 400 degrees, vaporize all the different parts of the mixture. The mixture of vapors pass into the fractionating column near fractionating column. Each fraction is obtained by collecting hydrocarbon molecules, which have a boiling point in a given range of temperature. For example, the fraction we know as petrol contains molecules which have boiling points between 30 degree and 110 degree. The molecules in the fraction contains between 5 and 10 carbon atoms. These smaller molecules with the shorter change lengths have lower boiling points and condense higher up to the tower. So the bigger hydrocarbon molecules with longer change lengths, it have higher boiling points and condense in the lower half of the tower. The liquids condensing at different levels are collected on trays. In this way, the petroleum is separated into different fractions. This process is known as fractionation. This fraction usually contains a number of different hydrocarbons. The individual single hydrocarbon can then be obtained again by refining the fraction by further distillation. It is processed to realize that the users of the fraction depends on their properties. Because, for example, one of the lower fraction which boils in the range of 250 to 350 degree, it is quite thick and sticky and makes a good lubricant, whereas the gasoline or petrol fraction burns very easily, which makes it a good fuel for use in engines. Okay, so in general, the properties of the fraction obtained from this fractional distillation change from the button on the top of the tower with this.
That's the top?
Yeah.
Okay.
Okay, and lastly, fossil fuels. Coal, petroleum, and natural gas are all examples of fossil fuels. The term fossil fuel is derived from the fact that they are formed from dead plants and animals which were fossilized over 200 million years ago during the Carboniferous era. So what is a fuel? A fuel is any substances which can be conveniently used as a source of energy. Fossil fuel release energy in the form of heat when they undergo combustion. For example, natural gas burned readily in air. So methane plus oxygen equals to carbon dioxide plus water. Natural gas, like petroleum, is a mixture of hydrocarbons. Methane is the main constituent of natural gas. It also contains ethane and propane, and may also contain some sulfur. The sulfur content varies from source to source. Natural gas obtained from the North Sea is quite low in sulfur. The perfect fuel will be cheap, be available in large quantities, be safe to store and transport, be easy to burn and causing no pollution and release no greenhouse gases, and be capable of releasing a large amount of energy. Solid fuels are safer than volatile liquid fuels like petrol, gaseous fuels like natural gas. How are fossil fuel used? So a major use of fossil fuel is in the production of electricity. Coal and natural gas are burned in power station to heat water to produce steam, which is then used to drive large turbines. A high proportion on the electricity generated worldwide is derived from fossil fuels. Coal is becoming less important while natural gas is increasingly important. So in power station, the turbine drives a generator to produce electricity, which is then fed into the national grid. The national grid is a system for distributing electricity throughout a country. And fossil fuels are an example of non-renewable resources, so-called because they are not being replaced at the same rate and the same tech rate as they are being used up. It is important to use non-renewable fuels very carefully and to consider alternative renewable source of energy for use now and in the future include nuclear, hydroelectric, biomass and biogas, hydrogen, wind, tidal, wave, geothermal energy, and solar. Okay, I think that's all for today. Thank you.
Okay. Okay, so let's come back to exothermic and endothermic reaction. So first, let's watch a video.
Different amounts of energy. For example, if you put the reaction in with the carbon dioxide, then each of the different molecules will play a different role. Or in other words, of each has different amounts of energy in it's important to also there's how much energy all the energy who has an energy products. In particular, the product has energy Now, the chemicals in the reaction and using energy electric and release because remember that energy can't be created or destroyed. It can be transferred from one place to another. And the most common way to exchange energy with the surroundings is in the form of heat. In this reaction, a lot of heat energy will be released. So if we had done it in a sealed container, then we'll be able to measure the increase in temperature as the reaction progresses and releases heat energy. We call reactions like this exothermic. And with all exothermic reactions have in common is that they transfer energy to the surroundings, usually in the form of heat. The most common type of exothermic reaction is combustion reactions, in which fuels are burned, usually in the presence of oxygen, like in oxygen. Other examples, though, include neutralization reactions between acids and bases, and most oxidation reactions. The opposite of an exothermic reaction is an endothermic reaction. These are reactions which take in heat energy from the surroundings. For example, if we wanted to break down calcium carbonate into calcium oxide and carbon dioxide, we'd have to supply it. That's by using a Bunsen burner to heat up the solid calcium carbonate. So if we wanted to draw a reaction for this reaction, then just like before, our reactants will be on the left and the product on the right. But this time the product will be higher up because they have more energy than the reactants. And so we label this difference as the energy absorbed rather than the energy released. So far, we've put both exothermic and endothermic reactions and looked at the reaction products which you might have to draw in examples. The last thing to cover is activation, which is the minimum amount of energy the reactant particles need in order to collide with each other. So the greater reactivation energy, the more energy that will be required to start the reaction. We can show this activation energy on our reaction profiles when we draw a curve from the reactants to the products to show how the energy changes during the reaction. Specifically, this increase in energy from the reactant's energy level to the highest points on our curve is the activation level. So as you can see, even in an exothermic reaction like this one, which releases energy overall, some energy is still required to get the reaction going in the first place. We can do the same thing for endothermic reaction profiles. Again, we draw a curve, and the activation energy will be the difference in energy between the reactant's energy level and the very typical curve. This means that if we want to show the same reactions, but with slightly higher activation energies, then we'll just make our curves a bit higher. Whereas if we wanted to show lower activation energies, we'll just make them a bit lower. Now, the very last thing we need to say is that if you're drawing a reaction profile for a specific reaction, like the ones we discussed earlier, then instead of just writing reactants and products on things, we can actually put the chemicals from our equations. Anyway, that's all for now. So hope you enjoyed it, and I will see you next time.
Okay.
Bye.
Wait, where is the stop recording? Okay, so I'm just going to summarize. Okay, so exothermic. This is exo. This is endo. Okay, so exothermic reaction is transfer thermal energy to its surrounding, leading to an increase in the temperature of the surrounding. And an endothermic reaction transfer thermal energy from the surroundings, leading to a decrease in the temperature of the surrounding. So, wait, let me draw that. This is exothermic. Let's pretend it's a fire. And the energy is going outside. So an exothermic reaction is hotter than its surroundings. And then this is an endothermic. Pretend it's an ice cube. The energy goes inside. Yeah. Wait, how do I move my... Okay. So we can conclude that the graph for the exothermic is like this. Let's draw exo. This is endo. Yeah. So an exothermic's graph is this is the reactant. This is the reactant, this is the product. So the reactant energy of the reactant is higher than the energy of the product. And for endothermic, wait. Okay, let's go. Endothermic reaction, the reactant is, the energy of the reactant is lower than the energy of the product. Okay, so
Okay.
the, 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 this is the activation side, activation energy. So from here to here, like how much energy do you need to surpass so that you can make a product? This is activation energy. Yeah, activation energy. And then this is the enthalpy change. I think you know enthalpy change, right?
Yeah, I know.
Enthalpy change. And for an endothermic reaction, the enthalpy change is positive, while for an exothermic reaction, the enthalpy change is a negative. So here, negative H. There. Okay, so let's have an example of whether this is a endothermic or an exothermic reaction. So for example, what yeah? Wait, CH4 plus O2, this is 2, is equals to CO2 plus 2H 2O. Okay. Plus, yeah. Okay. So the bonds, it will look like, wait, how does it look like? Oh, wait, never mind. Yeah, the bonds will look like this. So C, since there's 4H, yeah. So for each CH bonds, the energy per mole is 435. Okay. So then we can conclude that this one bond of this is 4 times 435, which is 740 kilojoules.
Yes.
Yeah.
Yeah.
Okay. And the O, since there's like, wait, how many O is that? Since there's like 2O2, so then it's going to be like this. But like since there's like 2 of these, then we just times one of these bonds, which is 497. We times it by 2. So then it becomes 994 kilojoules. And we plus it with the kilojoules from CH4. That is 994 plus plus 174 D for D, which is, how much is this? 2734 kilojoules, right? And then we go on to the making the bonds, which is this one. CO2 plus 2H2O. So CO2. CO. Translate this. Okay. So one of these bonds, the CO bonds, cost 803, but then there's 2, so we times it by 2. So it become 1606 kilojoules. And then for the H, for the 2H2O, O H. Okay, one of these cause 4, 6, 4. But then there's like 4 of these because like one bond, but then we times it by 2, so it's 4. 4, it becomes 1, 8, 5, 6 kilojoules. And if we plus this both, it becomes 3, 4, 6, 2 kilojoules. Okay. Okay, so the formula to find the enthalpy change. Yeah, enthalpy change is break bonds minus by making bonds. And you can see before that the breaking bonds is 2, 7, 4, 8, 2, 7, 3, 4, while the making of bonds is 3, 4, 6, 2. And then it will become negative 7 to 8. And since this is a negative, since this is a negative, in here, a negative is an exothermic reaction, and an exothermic reaction, the reactants have a higher energy than the products. So it's going to be like this. This is the product, the reactant, which is CH4 plus 2O2. This is the product. CO2 plus 2H2. This is in liquid, gas. This is in gas. This is also gas, same thing. And then this is the activation energy. And then this is the enthalpy change, which is negative 7 to 8 kilojoules per mole. Okay, so that's about the exothermic and endothermic reaction. So now let's go to chemical reactions. So uh, reactions. So first, physical reaction. Physical reaction will not lead to a new product, whereas a chemical reaction will lead to the formation of a new product. And all phase changes are physical change. Like from an ice cube, it melts to water. That's a physical change, not a chemical change. There is several indication for chemical reaction. First of all is the color change. Next is the precipitation formation. formation. Yeah. And then the evolution of gas, like gas suddenly appears. And then next is the energy change. So first of all, let's talk about the collision theory.
Mm-mm.
The collision theory. Wait, this is an S. Okay, so the collision theory is that when an element collide with another element, they make a new product, and that's the collision theory. But not all of the collisions that occur are successful collisions. Successful collisions means that a collision that form a product, because when they collide with each other, the this there is a specific energy that is needed, which is the activation energy, that can make a new product. It if the energy that is made during that process is not higher than the activation energy, then a product will not be made. And there's some factors that are affect the rate of reaction. First of all is the surface area. So when for example, limestone or carbonate. So when you grind limestones into like smaller pieces, it will have a much larger surface area that came in contact with another product that could make a new product. So for example, if we have okay, so this is a beaker, another beaker. This is a limestone that is not crushed. It's like this. And then this is a limestone that is crushed. And it came in contact with the same amount of another product. Let's think of it as something else. And then when it came in contact, misalkan for example, this is a water, right? It only came in contact with this part, not the part in the middle. So the surface area is much more smaller. Well, in this part, it came in contact with all of these.
Mm.
Okay. So next is concentration. So if you have a higher, okay, let's have an example of concentration. Okay, so this is a beaker. This is another beaker. Okay, so if you have, this is, for example, what can we do? For example, this is water, right? And then there is more water in this part than in this part, right? As you can see.
Yeah.
And it came in contact with the same amount of misalkan acid, right?
Yeah.
This acid will have more choices of making a bond with the water than this one, because this one it's like only a little bit. So if even if you pour a lot of acid, like the rest will go to in a waste. I know acid and water don't mix, like it doesn't make a new product, but pretend it does. Okay, and then another one is a catalyst. So a catalyst is like, how do I say? A catalyst is like a substance which alters the rate of a chemical reaction and is unchanged at the end of the reaction. So a, a catalyst, misalkan this is the activation site is this stall, right?
Yeah.
Like this stall, right? And then this is the activation site of when you use a catalyst. Why? Because a catalyst kind of makes another pathway so that the product don't need to use all that much energy to form it. The reactors don't need that much energy to form a new product.
Mm-mm.
Yeah. And that's it. Oh, okay. Reversible reaction. So I can't add another page. How do I delete page?
Oh, wait.
Wait, let me just
Oh,
pause.
okay.
There we go. Okay. Okay, so there is reversible reactions, which is a reaction that from a reactant it can go to a product, and from that product it can go back to the reactant. An example of this is hydrated copper sulfate. Hydrated copper sulfate will hydrated copper sulfate is blue, while anhydrated and anhydrous copper sulfate is white. Wait, let's just like this is an anhydrous copper sulfate. Okay, so for hydrated copper sulfate, there is water in this. That's why it will. That's why it is the color blue. Well, in this one, anhydrous copper sulfate, it doesn't have any water, so the color will be white.
Hmm.
And an example of it again is hydrated cobalt chloride. The color will be pink if there is water, while if there's no water, okay, yeah, the color will be blue.
Hmm.
And it will from here to go to here, it will be endothermic reaction. Well, if you go from anhydrous cobalt to hydrated cobalt, it will be an exothermic reaction. Okay. Um, I think that's it. Do you need to talk about the making ammonia?
Up to you.
Do you want to talk about it?
Yeah, sure. I will talk.
So for this one, the harbor process. So harbor process is the making of ammonia, and Henri Le Chatelier is a French scientist, and he noticed that if the pressure was increased in reactions involving gases, the reaction which produced the fewest molecules of gas, was favored. And if you see at the reaction of the Haber process, it goes from left to right, right?
Mm.
And so then the number of molecules of gas goes from 4 to 2. That is why the Haber process is carried out at a high pressure.
Mm.
And this guy also noticed that reaction which are exothermic produce more products if the temperature was low. So yeah, lower temperature favors the exothermic process. But if you do this, if you do this in a room temperature, you can get a higher percentage of ammonia. But in the practice, the temperature will be too low, and so the ammonia will not be produced quickly enough for the process to be economical or like to one, right? And you really need an optimum temperature to produce enough ammonia at an acceptable rate. And then a catalyst is used in this process. Iron catalyst is the one. Iron catalyst is the one that is used in this process. And I think, not I think, and they don't really use Haber process that much because yeah, the high pressure makes it expensive and it's more safety concerns for the workers. So they're like trying to find ways to have another process. Right now it's like involving biotechnology. Uh, and I think that's it.
Okay.
Thank you.
Thank you.